Alright class, let's cover the last part before our exam 2. So last thing we're going to talk about is periodic property. So far we've talked about electron configuration, we talked about covalent bonding, Lewis structure, valence electron. Now we're going to close this chapter by talking about periodic properties. Now, I'm hoping by the end of this lecture you have more appreciation for the way the periodic table is put together, because it's just beautiful. The first periodic property we're going to go over is atomic radius. Atomic radius is basically we're talking about the size. Atomic radius, we're talking about the size. Now, what we're going to talk about in this part of the class, we're going to talk about a lot of trends. The trend for atomic radius or for the size is as you go from right to left, they're going to increase. And as you go down the periodic table, they're also going to increase. So what does that mean? This is what it means. To kind of draw it out, to put it in perspective. Let's say here, let's see, I'm going to make this a little bit. This is sodium over here. I have sodium, I have potassium, I have rubidium, and I have cesium. So sodium, let's say if this is the side of cesium, the potassium size will be bigger. Rb would be bigger than that. Cesium would be bigger than that. So basically as you go down the periodic table, the sizes get bigger and bigger and bigger. And does that make sense? That makes perfect sense. Because remember what we talked about. This was n equal 1, n equal 2, n equal 3, n equal 4, 5, and then so on. Do you guys remember that? So as you coming down the periodic table, the n value increases, right? And if you remember, that's what we talked about before we're talking about all these things. We talked about energy level, right? As you go away from the nucleus, this is N1, N2, N3, and then keeps going up. As the number of N increases, the size has a bigger size. This is N1 versus N2. N2 is bigger, N3 is bigger, and it's exactly what's going on here. As you come down the periodic table, this N value increases. When the N value increases, okay, that makes sense. The sizes also increase. Now, I have a little conceptual question for you. Let's talk about cesium for a second. Cesium versus sodium. Which one do you think is more reactive? Basically, do you think the smaller guy is more reactive or the bigger guy is more reactive? So my question is cesium versus sodium. Which one do you think is more reactive? Now, here's a hint. Remember what we said? We said if you are bigger, that means your valence electron are far away from the nucleus. We said in the past that if nucleus is a mom and electrons are a kid, when the kid are far away from the mom, they can do bad stuff, right? Same idea here. When the atom is bigger, that means the valence electron are far away from the nucleus. When you're far away from the nucleus, you can play around. So which one do you think is more reactive? Yeah, cesium has more reactivity, because the valence electron can't really feel the plus charge anymore and they can play around. And a little fun homework for you guys. YouTube cesium in a bathtub. So some idiot years ago decided to take cesium and add it to his bathtub. Now, if you've probably done this in lab before, if you take a little bit of sodium metal and you add it to water, it's going to fizz around and it's going to dissolve. Now, imagine if you do that to cesium, which is a lot more reactive than sodium. So if you add sodium to water, it will smoke a little bit, it will fizz around. Now, if you add cesium to water, which is a lot more reactive than sodium, imagine what would happen. So some idiot thought it would be fun to take 1 kilogram of cesium and add it to the bathtub and blow up his house. People can do stuff that are dumb. Now, so yeah, that would just to kind of remember that cesium is really reactive. Now you might be asking me, okay, this makes sense. As we come down, they get larger and they get more reactive. What happens if we go from right to left? How would we explain that? Okay, let's explain that. In a same row, let's say I have fluorine and I have lithium. Okay, so I have lithium and I have fluorine. Lithium and fluorine, both of them are in a second energy level. So the size is the same in terms of the energy level. Okay. Now, why is it fluorine is smaller than lithium? Now, here's why. The number of proton for fluorine is 9, whereas for lithium is 3 proton. So when you have more proton, you can hold on to the electron tighter, right? You basically have more parents, more moms to hold on to the electrons tighter. So fluorine has 9 proton, which is lithium has 3 proton, more proton. I can hold on to the electrons tighter, and that's why fluorine is smaller than lithium. So as we go left to right, they get increased the size. As we come down, it will increase the size. Now, let's do a practice problem. You guys ready for the problem? I think you're ready for the problem. Here is our practice problem. What I want you to do, I want you to rank from lowest to the highest atomic radius. Okay? From lowest to the highest atomic radius. Here are the compounds you're ranking. Lithium, potassium, fluorine, barium, and Ga. I want you to rank this. Now, how would we rank this? Here's how you would do it. Every time I ask you to rank it, what I want you to do, I want you to write down, draw the trend. I go, okay, before I rank it, I'm going to draw the trend. Then put the elements relative to each other. Then put the element relative to each other. For example, I know I have lithium here and fluorine on the same row goes over here. And then I have Ga is right here. So here's I have fluorine, here I have lithium, same row. Ga is over here. And then I have potassium, which is in the same row as gallium, and then barium is going to be over here. So put these things relative to each other. Alright, so now let's rank them. Now the way you would rank it, don't forget, you should always look at up and down first before you look at left to right. Why is that? Because the energy values is what really matters. The higher the N value, the bigger the compound. So we have to look at up and down first. And if they're in the same row, then we look at left to right. So based on that, look at this first again. Look at this first because the N values really matters. So based on that, what is going to be my largest element is going to be barium. Do you guys agree? Okay. So barium is going to be the largest one. Now, what is going to be after that? Again, go row by row. So here's barium because you have to go up and down first and then nothing here. Then we're going to come over here. Now, these two, gallium and potassium, are in the same row. If you're in the same row, then you can look at here. Based on this, potassium would be larger than gallium. So then I'm going to have potassium. Then I'm going to have gallium. Okay. Now I'm going to come over here. Between lithium and fluoride are in the same row again. If you're in the same row, fluorine is my smallest one. It's going to be lithium. And then the last one is going to be fluorine. So here I went from the lowest, from the smallest, the lowest atomic to the highest. And hopefully you know this means greater, right? All right. So again, that was our practice problem. Put them relative to each other and then do this. Now, ready for the next one. So first one was atomic radius. Next one is ionic radius. Now, again, I'm going to teach you all the trend. The trend for ionic radius is the same as atomic radius. Okay? There is only one difference now. I'm going to write it down and we'll go over it together what that means. If you are on the same row, that means you have the same n value, right? If you're in the same row, you have the same n value, then charges matter. So if you're in the same row, you have the same value. If you have charges, the more negative you are, that means the bigger you are. Now I'm going to explain this one more time. So if I'm on the same row, I have the same n value, right? Now charges then matter. If the more negative you are, and negative, what does negative mean? Negative means you gain electron, right? So it makes sense if you gain electron, you are going to be bigger, right? If you gain electron, you are going to be bigger. Now, let's do a practice problem so you can see what I mean by that. Here's what I'm going to rank. Aluminum plus 3, sulfur minus 2. I want to rank this from the lowest to the highest ionic radius. Okay? Now, the same thing as before. The first thing I'm going to write down the trend. Okay? Then what I'm going to do, I'm going to put them relative to each other, right? Then I'm going to put them relative to each other. If I do that, I'm going to look at the periodic table. And then aluminum, again, you have to put them relative to each other. And then sulfur is more over here. Okay, let me draw this down. All right. Now, here's the thing. These are all on the same row. If you're on the same row, that means you have the same n value, right? Okay. Now, I said this is what changes for ionic radius. If you're in the same row, then charges actually matter. That means the more negative you are, you gain more electrons, so you are larger. Now, let's do what I mean by that. So they are the same row. Again, I'm going to explain this again, say it again. I know I'm repeating myself, but I want to make sure you really get this out. You're in the same row. If you're in the same row, plus you have charges, which is the case here. You're in the same row and you have charges, then remember, the more negative you are, the bigger you are. Okay? So we're on the same row and we have charges. So which one is going to be my biggest one? The one that has a minus charge, the S minus 2. So my biggest one is going to be S minus 2. Okay? What's after that? After that, now what's going to be my smallest one actually, before I even start? The smallest one is going to be my aluminum plus 3. So again, I'm looking at the charges. The more minus you are, the bigger you are. So that's going to be my biggest one. Now this one has a plus. Plus means you lost electron, right? That's going to be my smallest one. So if you're in the same row and you have charges, then the charges is what matters. Now, I also have sulfur and aluminum who don't have charges. If you don't have charges, then you go by the trend. So based on this, which one is larger? Aluminum is larger. Then I go by the trend if I have no charges. So it would be aluminum here, and then it would be sulfur here. So let me explain this one more time. If you're in the same row and we have charges, then the more negative you are, the bigger you are. If you're in the same row and you don't have charges like sulfur and aluminum, then you just go by the trend. But if you have charges, the more negative you are, you win. You're bigger because you gain electron. Now, having said all that, let's do another practice problem with this. here is our next practice problem. I want you to rank this, okay? These are ranking for the ionic radius from smallest to biggest. Rank this from the ionic radius. Again, the same thing. Again, you can pause me, do this problem, and then check your answer. The first thing that you do, you write down the trend. This is the trend for ionic radius. Then you go, okay, I wrote down the trend. Now what I'm going to do, I'm going to write the element relative to each other. The S minus 2 is over here. Cl would be next to it. Selenium minus 2 is over here. And then Br is next to it. So relative to each other, I'm going to put it down. And remember what we said, again, you always go up and down first. So these two are going to be larger than the other one because if the n value is what matters the most, right? The n value matters the most. So these two will be larger than this one. There's no question about it. Now, these two are in the same row. If you're in the same row and you have charges, then the more negative you are, the bigger you are. You don't go by the trend, you go by the charges. So these two, which one is going to be largest? Those two, the larger one is going to be selenium minus 2. Then it's going to be Br minus 1. Then I'm going to go to the next row. Now these two are going to be the next one. They're in the same row and they have charges. If that's the case, the more negative you are, the bigger you are. The more negative you are, the bigger you are. So then it's going to be S minus 2. And the last one is going to be Cl minus. Let's repeat this again. So what you're going to do, you're going to draw the trend. If there is no charges, that's great. The trend would be up and down first, then left to right. Now, if you have charges, again, the up and down, again, that gets priority. But if you're on the same row, and you have charges, then you don't look at the trend, you look at the charges. The more negative you are, the bigger you gotta be. If you're in the same row and there is no charges, then you will just go by the trend. All right. Nice job. Hopefully you got this done and we'll do more practice problems later. So next one. So far what we did atomic radius. Then we did ionic radius. Now the next one is going to be ionization energy. Ionization energy. I'm going to put IE. Ionization energy. Here's what ionization energy is. Ionization energy is energy needed to remove an electron. Energy needed because you need an electron. You need energy to remove an electron. So ionization energy will always be positive because you require energy in order to remove an electron. You require energy in order to remove an electron. Now, let me give you a couple interesting examples. Let's go to sodium. Sodium electron configuration is 1s2, 2s2, 2p6, 3s1. Okay? Now, let's say sodium plus 1. Sodium plus 1 would be 1s2, 2s2, 2p6. Do you agree? Sodium plus 1 means you're going to lose one electron. So you're going to lose this electron over here. Now, even though you look nicer and you look like a noble gas, when you lose one electron, you still need energy. It's 495 kilojoules per mole. I just looked this number up. So even though you look like a noble gas now, and this is favored, it's hugely favored, I still need energy to make this happen. Okay? I still need energy to make this happen. Now, let's see, I want to actually go to Na plus 2, which would be 1s2, 2s2, 2p5. Now now I'm messing with the stability. Right here, I look like a noble gas, I look beautiful. I'm messing with the stability. So how much energy do you think you need to be able to do that? A lot more. I need 4,000 565 kilojoules per mole of energy. I'm going to need a lot more energy to do that, and it's too large of the energy. That's why Na plus 2 doesn't really exist. That's too much of the energy to do. Okay, so you need energy to remove an electron. Now, again, we talked about it. All these things, I want you to know the trend so you can figure things out and compare them. The trend is the opposite for size. The trend is opposite to size. Does it make sense? Why is it opposite to size? It does make sense. Here is why. And I really want you to understand it. Does it make sense? It's opposite to size. So it's opposite to size. Now the question is, does that make sense? Why the trend is opposite to size? It does. And I want you to understand it, not just memorize it. So here, the size is smaller. Here, the size is larger. Do you agree? Because this is opposite of the size. Like fluorine was small, lithium was large. Okay. Now this makes sense. If you're a smaller atom like fluorine, that means your electrons are closer to the nucleus. So it's going to be much harder to remove the electron. That's why the smaller size, you're going to need more energy to remove the electron. Whereas here, these are the elements here, the atoms here are larger size. If you are larger size, that means the electrons are farther away from the nucleus, so it's easier to remove the electron. Because of that, the trend is opposite of size. Smaller size is going to be harder to remove the electron. I need more ionization energy. Larger size, it's going to be easier to remove the electrons because they're far away from the nucleus. So far, so good? Okay. Now, I want you to go based on the trend on our exams. But what I want you to know that there are exceptions. And we can explain the exception easily. Especially, I know you can do it based on what we've talked about in class. I'm not going to ask you for any exceptions, to be honest with you. As long as you know the trend and you can figure it out based on the trend, I'm happy. But I do want you to know that there are some exceptions and how you can explain the exceptions. All right, let's do an exceptions. Nitrogen and oxygen. Which one do you expect to have a higher ionization energy? Look at the periodic table and tell me. Nitrogen and oxygen. You probably are saying right now that you expect oxygen to have a higher ionization energy based on the trend, right? Okay. Here are the values that I looked up. Nitrogen, the value for nitrogen is 1,402 kilojoules per mole. Oxygen is 1,314 kilojoules per mole. So we expected oxygen to have a higher ionization energy, but in reality, actually, nitrogen has a little bit higher ionization energy than oxygen. But we can explain this. So nitrogen is 3p3, oxygen is 3p4. Okay, so we know that P has 3 rooms. We have 3p orbitals. Okay, right here it has 3 electrons. So 1, 2, 3. This one has 4 electrons in the p orbital. 1, 2, 3, 4. We can probably see where I'm going with this, right? Now, if oxygen loses an electron, it's gonna look really nice, doesn't it? If oxygen loses an electron, it's gonna have half-filled orbitals. It's gonna look prettier. Versus if I remove the electron from nitrogen, I'm messing with the prettiness. So that's why this is cost a little bit more to remove an electron. Has a lower ionization energy, is easier to remove this electron, because once I remove this electron, I look pretty, whereas here, when I remove the electron, I'm messing with the stability. So there are a lot of exceptions like this, which you could explain by writing down the electron configuration. But for now, I want you guys to go based on the trend. All right, ready for next one? The next one is electron affinity. So next one is electron affinity. Now, ionization energy was the energy needed to remove an electron. Now, electron affinity is an energy change to add an electron. Okay? So, ionization energy was energy needed to remove an electron. And you always need energy to remove an electron. Electron affinity is to add an electron. But I didn't say energy needed. I said energy change. Why did I say that? Here's why I say that. Because electrons' affinity could be positive or could be negative. You could require energy to do it. Or you could also release. Energy can be released to do it. So energy could be required or energy could be released. Now remember, if energy is not required and energy is released, this is actually favored. Why is this favored? Because not only you don't need energy, you're releasing some into the environment too. That's favored, right? Healthy smiley face. Oh, that was a creepy smiley face. I need to work on my smiley faces. There we go. A little better. Now, let's talk about 1A group. 1A metals and noble gases. They do not want to add an electron. Noble gases are already beautiful. They don't want to add an electron. The same thing with 1A metals. They want to lose. They don't want to gain an electron. So because of that, because that's not favored for them to add an electron affinity is required. You require energy to do that. Now, on the other hand, let's look at halogens. Halogens, they want to add an electron to look like a noble gas. Because if halogen add one electron, they're going to look like a noble gas. So this is favored. So not only energy is not required, some energy is actually released. Because it's a favored process to do. So ionization energy is always positive. Because you will always require energy to remove an electron. Now, adding electron, that's a different thing. You could sometimes require, for example, noble gases, 1A metals, because they do not want to add an electron. So then you need energy to make sure you do it. Now, there's some other atoms, like halogens, they want to add an electron. It's favored. They're going to look like a noble gas. So for those, electron affinity is actually negative. Negative is good. Negative, that means it's releasing energy. It's favored. Okay. Now, the magnitude follows the trend. And the trend is this. And again, the trend that I'm talking about is regardless of the plus and minus, right? The magnitude is follows by the trend. And the trend is, again, the same thing as ionization energy. The trend is the same as ionization energy. Okay. Now, ready for next one? Again, the trend is the same as ionization energy. Again, if this follows the trend, regardless, the plus and minus doesn't really matter. The magnitude will follow the trend. Now, the last one, which I'm not actually going to go over it because we've done this before. Go over the bonding part 1 to look at this. Electronegativity. I'm not going to go over it again. Go back to your notes for bonding part 1. Electronegativity, we talked about it, that different atoms on a periodic table have different strengths. Some atoms are stronger than other atoms. And the trend for electronegativity, which is how strong an atom is over here. That's the trend for electronegativity. Now, I want to summarize everything. So the trend for size was this. This was a trend for size. And the trend for everything else was the opposite of that. For ionization energy, for electronegativity, for electron affinity is the opposite trend. And we explain why that is. Okay, now, are you ready to do a practice problem? Let's do it. Let's do a practice problem to make sure you get this down. Here are our practice problem. Pause this and do this. You're going to rank these atoms from the lowest to highest electron affinity. Okay, so hopefully what you did, hopefully you said, the first thing I'm going to do, I'm going to write down the trend. What's the trend? The trend is going this way and the trend is going this way, right? And then the next thing you're going to do, you're going to say, okay, I'm going to put the elements relative to each other. Okay, put the element relative to each other. So way on top, I'm going to have Si somewhere here. Again, they have to be relative to each other. And then I'm going to have zinc. And then cadmium is going to be right here. And then Ag is going to be next to in the same row. And then nickel is going to be over here. Again, relative to each other, you're going to put the element relative to each other. And again, we said it before. Up and down really, really matters, right? Up and down really matters because the n values make a huge difference. And then here's my trend. So based on this, which one do you think is going to have the highest electron affinity? Silicon over here, right? Silicon is going to have the highest electron affinity. So I'm going to put Si all the way here. Now what's after that? So silicon is going to be the highest one. Then when you come down here, these two are on the same row, right? If they're on the same row, then which one is going to have the higher one? Same row, this is a trend, so Zn is going to be higher than nickel. So then I'm going to have Zn, then I'm going to have Ni, then I'm going to come to the next row. Okay, again, these are the lowest one based on this. They're on the same row based on the trend, the cadmium would be higher than silver, right? The cadmium would be higher than silver. Again, if you look at this, if you're over here, you're the largest one. When you're down here, you're the smallest one. And this would be the ranking for those. Alright, nice job. The next video, we're going to do nothing but practice problem to get you ready for the exam. Nice job.